What we have to go over today, as shown up on the smartboard, is double displacement reactions. So as you notice on the bottom of this page, or I guess in the middle, what makes a double displacement reaction different than a single displacement reaction is there's two compounds. Heck, those trays are already set up for you as well, because it's the lab we're doing next time. You see all these little dropper bottles here? You're basically going to be mixing a little bit of this with a little bit of that over and over and over and over again. There's going to be like 40 different combinations that you're testing out next time. And then we'll do a little bit of extra stuff with one of the combinations at the end. But it's no longer just a metal or a single element in a compound. It's two compounds. However, similar to single displacement, it is a displacement reaction, which means, as I've written here, there's going to be a switching that takes place. So we can look at it as the lead and the potassium switching. Now, you could say the iodide and the nitrate switching. It's the same thing. But we're going to have a switch occur. Just like with single displacement, when you have a switch that occurs, you have to make sure to rebalance formulas. And what I mean by that is potassium is now going to be with nitrate. Well, what's potassium's charge? +1. What about nitrate's charge? -1. So then, that would be the formula, not KNO3 2. Again, we have to rebalance the formulas. My other compound then would have lead, which this lead is a +2 charge. I know that because there's two nitrates with it. Iodide's a -1. So this would be PbI2. At that point, if I erase my switch, I'd have to rebalance the equation. So for example, put a K here, or I'm sorry, 2 there and a 2 there, and now my equation is balanced. I still would have to figure out the phase notations for these two compounds. And that's something I'm going to go over with you in about 5 minutes or so. But for now, I can tell you that the potassium nitrate would be aqueous, and the lead 2 iodide would be a solid. Now again, I was gone the day that Mr. Butters went over the reaction types with you. But one of the things that either then or in particular today that we have to emphasize, just like in single displacement, it doesn't always occur. You put a metal in a solution, it doesn't mean it reacts. That's what you have that activity series for. The same thing holds true with double displacement, that not every time that you mix two solutions together will it react. How we know it will react is it creates a solid. A change occurs. That solid, when two solutions are mixed together, is called a precipitate. We actually did a lab where we added two solutions together and we measured a ruler how much precipitate different test tubes had. So we have to be able to make that precipitate in order for that reaction to occur. And that's what I'm stating on the top here, is that in a double displacement reaction, if you add two solutions together, something that you create can't be aqueous. And I'm going to kind of show you why here on this slide. Two compounds. Emma, give me one of the products of this reaction.
Sodium nitrate.
Sodium nitrate. I'll tell you right now, that would be aqueous. Max, what would be the other product then?
Lithium chloride.
Lithium chloride. Tell you right now, that would be aqueous. One of the things that we went over last class, and we're going to do more of today, is a reminder of what's called net ionic equations. For example, NaCl aqueous is really sodium ions and chloride ions just floating around. Remember, if I asked you to draw the dissolving of sodium chloride, that's kind of what you do, is draw Na plus surrounded by water, Cl minus surrounded by water. This is just a brief representation of that. Lithium nitrate aqueous is lithium ions, nitrate ions. Sodium nitrate is aqueous. Lithium chloride is aqueous. So this would be the total ionic equation for this particular reaction. If we were to write the net ionic equation, one of the things I told you last class is you eliminate spectator ions, things that are identical on the left and the right side of the arrow. Colton, can you give me one spectator ion in this reaction?
Sodium.
Sodium. Here's Na plus aqueous. Here's Na plus aqueous. It's the exact same. So in other words, it kind of cancels each other out. It did not change. Frigno, give me another one. The chloride. Here's Cl minus aqueous. Here's Cl minus aqueous. Identical. It did not change. It's not part of the overall net reaction. Ashley. Lithium. Li plus aqueous, Li plus aqueous. Creighton. Nitrate. If all I did was mix two solutions together and get two solutions in return, nothing happened. You could rewrite these formulas however you want. It doesn't change the fact that nothing actually changed, which is why one product can't be aqueous. That means a change would actually occur. Well, how do we figure that out? We look at the bigger part of this sheet that you used before. So this sheet, you wrote on the far right-hand side above activity series, single displacement. Now where it says table of solubilities, I want you above that to write down double displacement. So again, find the sheet that you were working on just a little while ago when we were doing single displacement reactions. Now, your sheet is slightly different than the table that I have up here. On the upper left-hand corner of your sheet, so yours right in this area, it says an I is insoluble and S is soluble. If you are soluble, take, for example, look at your table. Aluminum and bromide, right? You're almost playing Battleship. You have this side, you have that side, aluminum and bromide. What letter do you see when you bring aluminum and bromide together on your table? S. And S means soluble. Now on my table, I have it written as AQ because if you're soluble, that means you're a solution. You could be dissolved. Aqueous things. However, if you go one back, aluminum acetate, you see an I. And an I means insoluble, or you create a solid instead. Here's what I want you to do for about 2 to 3 minutes to kind of help out organizing this. Our goal when we look at double displacement reactions is we need to find a product that is a solid. Something that's insoluble. And I apologize for the fact that your table has I for insoluble and S for soluble, because some people want to think S is for solid. But here's what we're going to do to try to help out with that. You're going to, and again, you could use pencil, you could use a highlighter. Heck, I have colored pencils in the back of the room if you want to do that. I want you to take a couple minutes and highlight, mark, whatever it is, every single I on this table. because the I's are what we want. Because if it creates something that's insoluble, that means a chemical reaction has occurred. So, take a couple minutes and do a little coloring. You're highlighting, shading, whatever it might be, the I's on that solubility table. As you are finishing up your highlighting, again, I like to treat this table like the game Battleship, where if you call off B8, you are looking for, is it a hit? Did I hit a highlighted spot on my table? Because if so, I created a precipitate. And you're going to see plenty of those next time. It's that cloudy solid that forms when two solutions come together. If it did not create a precipitate, well, then look at the other product. Because in a double displacement reaction, we need at least one thing not to be soluble. We need one thing to create that precipitate, typically, is what we're going to see in the lab. Some students will ask, can both products create something insoluble? Possibly, but it's hard to do when you have two solutions to start with. But if you start with two solutions and you end with two solutions, nothing has really happened. You're just mixing stuff together. It's taking Mountain Dew and then all of a sudden adding some vinegar to it. They're two solutions. It's not going to chemically react. It's just going to now have two things. Plus now you've ruined your Mountain Dew. Some students will even look at a few things like the nitrate column. Things that end in NO3 never create a precipitate. So sometimes that helps them out, that they know they only have to look at that one. Looking across, ammonium never creates a precipitate. Sodium, potassium, so those alkali metals don't either. Some students will ask about the X. Now your table says compound does not exist. So for example, aluminum sulfide should not ever be an option because you're not going to see that combination ever. But what we need to do now, just like with single displacement, we need to practice how to use this table. My hope is you can find the two worksheets from last class that we did the top half for each time. Well, now we're going to do the bottom half for it. So you're looking for the worksheet that had a 1 through 4 on the top and the bottom. The 1 through 4 on the top, you already did. The 1 through 4 on the bottom is what I'm showing up on the smartboard right now. If you can't find it, then you're just going to have to look at the smartboard. But there's two different worksheets that we're going to be working on dealing with single and double displacement reactions. So to start with, on this worksheet, again, we're looking at the bottom 1 through 4 if you have it in front of you. Otherwise, you're looking up at the smartboard. I give you two solutions to start with on the reactant side. Notice how there's question marks where the phase notation is. That's what this sheet of paper is for. This sheet of paper is to figure out the phase of the products. For example, if you look at potassium bromide, KBr, find potassium on that table of solubilities, so look on the left-hand side, find bromide on the top, bring your pencil together, do you hit a highlight? No. That means potassium bromide would be aqueous, which potassium always is going to make things that are aqueous. How about calcium and hydroxide? Find calcium, find hydroxide, bring them together. I'm seeing people nod their heads yes. That creates a solid. When I ask whether or not the reaction occurs, if it creates a precipitate, the reaction occurs. Calcium hydroxide is a solid. That's a precipitate that would be in solution. Let's look at the second one. Aluminum sulfate. Does that create a solid? Look at your highlight. Aluminum sulfate. Seeing people shake their head no, that means aluminum sulfate would be a solution. Again, if it's not one of your highlighted boxes, that is soluble. Again, on your solubility table, S stands for soluble, which means it's a solution. Sodium nitrate. No, it does not. If I have two products that are both aqueous, that reaction does not occur. Okay? On your own, take about 2 minutes right now to answer questions 3 and 4. Now, if you answer yes, it will occur, the why question would be identifying which product created the precipitate. This worksheet is very similar to a single displacement reactions worksheet you did last time. And just like last time where I basically said there's a lot of text that I'm not going to read and I'm just going to go over the backside of it with you, that's what I'm about to do right now. Is I'm not going to read all this text on the front side. Instead, I'm going to do the backside with you. So, it does mention total ionic equations and net ionic equations. It gives an example here that doesn't actually occur, which is very similar, if not the exact same example I gave early in class. I want to do this problem on the bottom backhand side with you right now. Again, our last goal of today is, now that we're hopefully starting to get used to writing chemical equations, can we write the total ionic? Because anything that deals with a solution, we have to recognize when we write NaCl aqueous, that's a simplification. It's actually Na plus ions floating all around, Cl minus ions floating all around. And then can we identify the net ionic, the change that actually occurs? So in this particular problem it says, copper 2 sulfate solution is added to sodium sulfate solution. All right, so my formula for copper 2 sulfate is CuSO4. Sodium phosphate is Na3PO4. So you can always write down the reactants to start. Figure out how to do your naming so you write the correct formulas. Sodium was a +1 charge, phosphate was a -3. And if you struggle with naming, we got to get you working on that, because writing balanced equations will not go away this entire unit and for the majority of next unit as well. Okay, do we have our solubility table out? Let's play Battleship hit or miss. Sodium sulfate. Will that create a solid? Sodium and sulfate. I've seen people shake their heads no. I'm going to write down that product. Oh, I'm going to write down that product incorrectly. What should be the formula of sodium sulfate? Na2SO4. Copper 2 phosphate. Does that? I see already someone shaking their head yes, so that one does occur. I'll write that formula incorrectly. So I put the copper 2 and the phosphate together, but now I have to cross and drop however you think you need to do it. That would be the formula of copper 2 phosphate. Now, I have to balance the equation as a whole. For example, I have 3 coppers on the product side. I'm going to put 3 coppers on the reactant side. But now that gives me 3 sulfates on the reactant side. I'm going to put 3 sulfates on the product side. That gets me 6 sodiums on the product side. Now I have 6 sodiums on the reactant side. 2 phosphates on each side. This equation, a little bit more work, but is now balanced. And remember, I would balance based upon polyatomic ions. Notice how I said 3 sulfates, not 3 sulfurs and then 12 oxygens from this and another from that. Based upon polyatomic ions when we're dealing with displacement reactions. Okay, total ionic. Take the things that are aqueous and break them apart into their ions. For example, I have 3 copper plus 2 ions and 3 sulfate ions. So what I've just written is breaking down the CuSO4. Quite frankly, it's similar to what I just did to balance the equation. How many coppers do I have on each side? How many sulfates do I have on each side? How many sodiums do I have? 6. 2 times 3 is 6. So I have 6 Na plus ions, and I have 2 of the PO4. Please remember to include the correct charges. Sodium's a +1. You don't have to actually write down the 1. Phosphate is a -3. Once again, on the product side here, I have 6 of the Na+, and I have 3 of the sulfate. But then we get to that last product in this problem. The precipitate, the solid that's created, is not ions in solution. That's what aqueous means. When I write Cu3PO42, what happens is those ions, all in solution, kind of stick together and form a solid, a cloudy solid that's in that solution. And if you remember when we did that test tube lab, we created those. You'll see definitely a lot of it next time. But because this is not aqueous, we can't break it apart. You keep this held together. Cu3PO42 solid. This would be the total ionic equation for this reaction. Similar to single displacement in that we break apart aqueous things and we still have solid thing in there. Different in that one of our compounds stays stuck together. Because it is not an aqueous solution, which means ions floating around. It's 2 ions that stick together. And when they stick together, they don't break apart anymore. Once again, similar to what we did with single displacement, we now eliminate spectator ions. Caden, can you find 1 spectator ion on this total ionic? It's the exact same on the left and the right side of the arrow.
Sulfate.
Yeah. SO4. There's 3 of them here, there's 3 of them there, it's identical. Rogers, there's only one other one. The sodium. Just like with single displacement, when you write your net ionic, you cancel out the spectators. Now, I apologize that I don't think I can get my screen much higher here. So this might be low, so I might be starting to see you guys doing this to look at the answer. Now, heck, I'll just write it up here. You have 3 of the copper plus 2 ions. Sorry that I'm writing vertical here, but I think it's better for you to see it than down there. Plus 2 of the phosphate ions will create Cu3PO42 solid. In a double displacement reaction, the net ionic is which ions create the precipitate. That's solid. that sticks together. Just like the lab that you turned in today, next class, the lab that you do, will have a lot of chemical equation writing, but we will also assess your ability to do total and net ionic.